Cryptography. The science of securing communication. Cryptography can help us keep our secret secret. It's a big part of the confidentiality leg of the CIA triad. This is what most people think cryptography does and nothing else. But it can also help us ensure that our data is unaltered. That provides us integrity. And we also use it for authentication for our subject, and it can provide non-repudiation. Cryptography has been used for thousands of years to keep our secret secret. So for the exam, you need to know a good part of the history of cryptography, as well as current uses for it, how it works together, the advantages and disadvantages of different types of cryptography, and how and where we would deploy it. And as with everything else we do in IT security, we need enough encryption, but not too much. We want our encryption to be strong enough to be unbreakable, or at least take an unreasonable amount of time for it to be broken. If it's going to take an attacker 10 years to decrypt our message, we're probably okay. But it needs to be a clear balance between confidentiality and availability. The stronger encryption we use, the longer it's going to take to encrypt and decrypt. In cryptography, we use a lot of modular math, and for the exam you need to know what it is, but you don't need to know how to do it, which is good news. Think of it as numbers wrapping around, or looping, every time they reach a certain value, or a modulus. This is also why it's called clock math. If we use the English alphabet as the modulus, it has 26 letters, and we assign direct number values to the letters, so the letter X would be number 24, and the letter E would be number 5. In linear math, that would be 29, but since we use modular math, numbers wrap around and start over. So once we get to 26, we start over with 1. That way, if we add an X and an E, we get a C. This is a very, very basic example of modular math, and you'll see later the numbers they actually use are much, much higher. But just understand the concept of how it works. Let's start out with some definitions. Cryptology is the science of securing communication. And for the exam, I would know the definition of all these, just again at a high level, but be able to differentiate them and be able to briefly explain what each of them means. Cryptography is creating messages where the meaning is hidden. Cryptanalysis is the science of breaking the encrypted communication. The cryptographic algorithms we use now are often very hard, or if not impossible, to break, and as anywhere else, the attacker is going to look for the weakest link. They don't need to break the encryption if they can find the encryption key on a server somewhere. In cryptanalysis, we both use mathematical analysis to attack the cryptographic algorithm, but we also use side-channel attacks, where we try to exploit weaknesses of the implementation of the cryptography or the devices that run it. And then finally, a cipher is a cryptographic algorithm. So understand these 4 key terms and be able to briefly explain what each of them entails. Also understand that the plain text or the clear text is an unencrypted message. That's the secret we want to keep secure. Whereas the ciphertext is the encrypted message. And we use encryption to convert the plain text into ciphertext. And then the other way around, we use decryption to turn the ciphertext back into plain text. Let's look at some of the older types of encryption, how they were used and what they do. I think we've all seen the movies where the villain or a hero gets a piece of paper with a random string of numbers, and they go looking through their bookshelves and finds the books and deciphers the message. That's a book cipher. Both the sender and the receiver has the same book in the same version. The book is the decryption and encryption key. Sender would send 244.2.13, 12.3.7, so on. And the person receiving the message will then go to page 244 of the book, sentence 2, word 13. That would be the first word of the message. Then it will go to page 12, sentence 3, word 7, and so on. I would assume they're not really used anymore. A running key cipher, the sender and receiver would agree upon a phrase they would use as a running key cipher. For instance, they use the IC² Code of Ethics preamble, the safety and welfare of society, and the common good. The sender would then take their plaintext message, add the preamble to the plaintext. Think of it similar to the modular math, where it wraps around. Once we reach the end of the preamble, we just start again. That will scramble all the letters. The receiver would then take the ciphertext, subtract all the letters from the preamble, and they would get the plaintext. It's just simple addition and then subtraction. Mono and polyalphabetic ciphers have also been used extensively in the past, but today they're obviously easy to break. A monoalphabetic cipher, you just replace one letter for another, and it's really easy to break with frequency analysis. If you look at the image on the right, you can see that E is the most common occurring letter in the English alphabet. It occurs 12% of the times. 12% of the letters are E's. So if we have a long enough text, we can start deciphering letters just by looking at their frequency of occurrence, even if we didn't use the frequency analysis. Since every letter substitutes for the same letter every time, we will very quickly see patterns emerge where the most common words be used over and over again, and from those we can decipher what other words might be. Polyalphabetic ciphers are slightly more secure because each round on encryption, it uses a different starting point. So on the first round, T might be a W, but on the second round, it'll be a D. Obviously more secure, but still very easy to break today. And as I mentioned, the frequency analysis is just analyzing how often a letter occurs in a certain ciphertext. And with enough ciphertext, you might be able to break it and get the plaintext. In XORing, or exclusive OR, we add a simple key to a plaintext to make a ciphertext. It's very useful in basic cryptography and really just deals with ones and zeros, which all data is. It's very commonly used in symmetric encryption, or at least in the algorithms behind them. I've had some students struggle with this, and what's helped them the most is looking at it not as numbers, but as true or false. 0 is false, 1 is true. Or just remember it by if the numbers are the same, it's a 0, if the numbers are different, it's a 1. The 00 turns into a 0. The A is the plaintext, the B is the XOR, and then the output is the ciphertext. 01 would turn into a 1, 10 would also turn into a 1, and 11 would turn into a 0. If it doesn't make complete sense to you right now, don't worry about it. I think it will later when we start looking at some practical examples of how we use it in symmetric cryptography. When we use XORing, we want confusion. What that really means is, if you have the plaintext and the ciphertext, it should be as random or confusing as possible. It shouldn't be possible to discern any of the plaintext from the ciphertext. We also want diffusion. That's how the order of the plaintext should be diffused and dispersed throughout the ciphertext. We also use substitution. So to get that, one character is replaced by another, thereby giving us the diffusion. And we use permutation or transpositioning, where we rearrange the characters of the plaintext, thereby providing the confusion we want. Over on the bottom right, you can see a plaintext, a key, and the ciphertext. And remember, this is done on a bit level, so it's all zeros and ones. For each column of plaintext and key, if they're the same, the ciphertext will be a 0. If they're different, the ciphertext will be a 1.